Daily, we do so many types of works. After getting from the bed, our work starts like brushing, bathing, eating, listening, answering, going to bus, running. Once come to school, listening to teacher, writing on the notebook, eating. Like we do so many activities in a day. Like some of examples I have drawn here: walking, jumping, reading, eating, fighting, watching a TV, etc. And we believe that all these are works. Exactly. At this moment, I'm teaching you, so I'm doing work, and you're watching me, you're also doing work. So all these are works. But do you agree with it in physics? Not at all. Because physics says, if you want to tell something in physics, it should be measurable. If it is not measurable, that is not physics. So work also be measurable. Now how it can be measurable, and how can we say that this is work and this is not, and what is the relationship between energy and power with work? We're going to discuss in detail in this chapter called work, energy, power. So what is work? See the example here. There is a body of mass M. It is at point A. It is in rest state. Now force F is applied on the body. Then the body started moving to point B. And it has traveled a distance S. Then work is defined as it is the product of force and displacement in the same direction. So work is defined as it is the product of force and displacement in the same direction. This is the definition of work. So the formula is W equals to force into displacement. See, force is a vector, displacement is also a vector, but work is not vector. Work is scalar. It has only magnitude, there is no direction. So the formula is W equal to Fs. Now, if you ask me, the SI unit of work is joules. Joules, or you can write capital letter capital J. But 1 joule equals to F into S. So 1 Newton into meter. So work unit can be joule, or also you can say Newton meter. But if you ask me the SI unit specifically, it is joule. Now coming to this example. A body is falling to the ground. Falling to the ground from a height h. Can you calculate work done on this body? Really, it's possible? Yes, it is possible, because here the force is there. What force? It is as falling freely, the force is force of gravity, or the gravitational force by the earth. So the amount of work done by the gravitational force on the body M is W equal to Fg into H. It's perfect. Is it possible to calculate work done here? Yes, of course. Here the body is pushed up to a height h. When you want to push up, it doesn't go automatically. You need to apply force. So this force is opposite to the gravitational force. So the amount of work done, W equals to F into H. So in all these cases, you can find work done. The only difference is, here I use the symbol S, here I am using the symbol H. But all are same, but different situations. Now see, we understand about what is work. Now there are two types of works: positive work, negative work. Positive work. So when we say it's a positive work, when force and displacement both are in the same direction. Mathematically, we can say force is parallel to displacement. See this example here. A body of mass 2 kg at this point A, a force 6 Newton applied on it, and the body moves in the same direction. So force direction, body direction are same. Then the work done, W equals to F into S, which is a 6 into 3, 18 joules is the positive work. It is positive work. Now coming to second one, negative work. When force is one direction, displacement is in opposite direction. In mathematically, we can say force is anti-parallel to S. See this example here. A car is moving towards the right side with its engine force of 18 newtons. But there is a frictional force acting on the body. Means where? Between the tires of the car and the road. And the car traveled distance of 2 kilometers. If they ask the question, though, what is the work done? What is the work done by friction? If I ask you, friction is opposite to the motion of the car. So therefore, W equals to minus F into S. So minus, the friction value is 2 into displacement is 2 kilometers. You convert into meters, which is 2000. So minus 4000 Newton. Sorry, minus 4000 joules is the amount of work done. And this is negative work, because friction is opposite to the motion of the car. So negative work. So that's how we can differentiate positive work and negative work. To add more, if I ask what is the work done by the engine force, what is the work done by the engine force? So engine force 18 Newton. So therefore, W equals to F into S, which is 80 into 2000 meters. So this is almost 1640 joules. It's a positive work because this arrow body is moving in the same direction. Now if you ask a question, that see how the different questions can be asked. Work done by the net force. Net force, we discussed in the previous chapter that net force is a resultant of the forces. So one force is 80 Newton, other force is 2 Newton. The net force is 80 minus 2, 78 Newtons. So W equals to force net into displacement. Force net is F minus small f into S. So 80 minus 2 into displacement is 2000 meters. So how much it is? 78 into 2000 equals to 0.006 156,000 1,56,000 joules is the net amount of work done. See, this is the work done by the engine, this is the work done by the net force, and that's the work done by the frictional force. Now let us discuss about one more interesting concept called zero work. That means work can be positive, can be negative, sometimes work can be zero also. How? The small story I will tell you. In the railway station, the Mr. P got down from the train, standing on the platform with a large suitcase. So while passing, a railway coolie approached him and asked him to lift the luggage. Then Mr. P told him that yes, you can lift the luggage and please bring to outside the railway station. Then the coolie put the luggage on the big suitcase on his head and walked across the platform, and he came out of the platform and put the luggage on the ground. Then Mr. P told, "Thank you very much," and he's going. The coolie stopped. Sir, pay me the work what I have done. The Mr. P laughed at him and he said, you have done zero work, so I do not pay you. Then there is a fight between Mr. P and railway coolie. Then who is the right one here? Mr. P is correct one or the railway coolie is correct? To know this, let us discuss about zero work. As we know that work W equals to force into displacement. Work can be zero in three cases. One, F equal to 0 implies work can be 0. F equal to 0 means don't think that S is 0. S is not 0. Only force is 0, but S is there. The force applied on the body is 0, but displacement is there. Still work is 0. How it is possible? See, when F equal to 0, according to Newton's second law, ma equal to 0 implies A equal to 0 implies what is acceleration? Change in velocity by time. That means change in velocity v minus u equal to 0 implies v equal to u. So what you understand with this? Force is 0 when body moves with the same velocity, which is called constant velocity. So any car moving with constant velocity, v equal to constant velocity, then it doesn't feel any force. Then it doesn't do any work also. So this is the first case. Now second one, when displacement is 0, s equal to 0 implies there also work equal to 0, because keep s equal to 0 here, w equal to 0. But f is not 0 here. Means you are applying the force, but the body is not moving. For example, you are looking at me, I am applying force on the board. I am applying force with my hand. But do you think the board is moving? No. So force is applied, but there is no displacement. Then we say this work done is 0. And the third one, very interesting case, when force is perpendicular to displacement. Force is perpendicular to displacement means when the angle between displacement and force is 90 degrees. In that case also work done is 0. Why 90 degrees 0? You get to know when you go to higher classes, because this formula actually Fs cos theta, but in your level we discuss only W equal to Fs. So when you go to higher classes you get to know more things. So when force and displacement are perpendicular, work done is 0. Now come back to the story here. Mr. P has told that you didn't do any work, I don't pay you, because the coolie kept the luggage on his head. The luggage has weight, is acting downward. The weight is gravitational force, yes. But how the railway coolie is moving? He is moving horizontally on the road. When moving horizontally on the road, S is horizontal. Therefore, the angle between them is 90 degrees. And the 90 degrees, as I said, W is 0. So that's why he is a physicist. That's why he said that there is no work. Of course, it's for fun, we can take it, but you should know that we have to pay the money. We understood that the work in physics we need to take which is measurable, and that you can measure using the formula W equal to Fs. But the question is, if you want to do work, what you require? Yes, you require energy. If you want to do 12 joules of work, you should have minimum 12 joules of energy. If you want to do 100 joules of work, you should have 100 joules of energy. So actually we say work and energy are interchangeable. How much amount of energy you have, that much amount of work only you can do. You have 100 joules of energy, you cannot do 150 joules of work. It's not possible. It is opposite to natural laws. So it's not possible. So how much of energy you have, that much of work you can do. So that's why energy is defined as the capacity of doing work. So it is the capacity of doing work. That's the energy definition. It's a very simple definition. And work and energy both are same, interchangeable. You can interchange. So therefore both have same SI unit, that is joules. Now the question is, how many types of energies we have? Plenty types of energies we have. Let us list down the types of energies. Types of energy. Yeah, so we have mechanical we have. Next, solar, that's correct. Nuclear, light, electricity, wind, or how many you have? Geothermal, etc. If I start writing, it will take more than 1 hour to write the types of energies we have. This is the basic energies we have. We can say sound energy, magnetic energy, all are energies only. But here our basic discussion, main discussion is mechanical energy, the energy which is produced due to mechanical force. So mechanical energy. So energy is produced due to mechanical work, and these mechanical energies are two types. One is kinetic energy and other one is potential energy. Kinetic and potential. You are walking on the road, you are running, then what type of energy you have if you want to do is walking and running. So while you are walking and running, the energy you generate is kinetic energy. See, I am throwing the marker in upward direction, throwing the marker. When you want to throw in the marker, the energy generated by the marker is potential energy. So how can we classify kinetic energy and potential energy? So the definition is kinetic energy is generated when the body is in motion. So it is generated when the body is in motion. So if you take a body of mass m moving with velocity v, then the kinetic energy formula is given by half m v square. K equal to half m v square. This is the formula to calculate kinetic energy. Now coming to potential energy. So when do you generate potential energy? As I said, when I throw the marker up, the marker has potential energy. That means it is the energy generated when you change the position of a body against the gravity. Against the gravity. Changing position against gravity. Against gravity. That's why sometimes this potential energy is called gravitational potential energy also. So there is a ball of mass m you have thrown upward to a height h. To a height h, for example. Then the potential energy is given by mgh. M is the mass, g is the acceleration due to gravity, the constant value 10 meters per second square, h is the height thrown. Sometimes it is also called gravitational potential energy. Potential energy you can also generate in different ways. When you change the shape of the body, or when you change the size of the body, also you can generate potential energy. You take a paper and you crush the paper. Take a cup, crush the paper cup. The size is changed, shape is changed. That means you are generating the potential energy. One more good example. Take the rubber band and stretch it and you leave it. And what happens? The rubber band comes to its initial state again. It is because the rubber band, when you stretch it, it generates potential energy, and that energy makes the body comes back to the initial state again. So potential energy is also called the energy stored inside the body. Each and every body has potential energy inside. And this potential energy can be converted into many ways: kinetic energy, sound energy, light energy, electrical energy, magnetic energy, nuclear energy, etc. We learned about kinetic energy formula, which is half mv square, and potential energy formula, which is mgh. Now we're going to derive those formulas and let you know that how those formulas have come. The first one, derivation of kinetic energy. Let us take a body of mass m. It is at point A. Its initial velocity is u, and it has traveled to point B. Its final velocity is v. Let the distance traveled is s with acceleration a. If you apply kinematic equations here, the kinematic equation, you can use v square minus u square equals to 2as. So this equation we know already, we learned. Now you multiply both sides by m divided by 2. So m by 2, which is half the mass, v square minus u square equals to m by 2 into 2as. So that the value doesn't change. Now if you take m by 2 inside, you will get mv square by 2 minus mu square by 2 equals to 2 to cancel, you get ma into s. Ma is the force F into s. So F into s is nothing but work done. Now it's coming to here, mv square by 2, which is called ke2, kinetic energy final, minus ke1, kinetic energy initial. So this form, if you see, it is called work energy theorem. Work energy theorem. It says the amount of work done is change in kinetic energy. Amount of work done is change in kinetic energy. Okay, our concept is we need to derive the kinetic energy formula. In this, let us assume that the body starts from rest. When the body starts from rest, initial velocity u equal to 0 implies half mu square equal to 0. Implies, if you see this expression here, then what happened? ke2, which is equals to w. So in general we write ke2 as ke, which is half m v square. So this is how we got the formula, kinetic energy formula. Now you can see here we are trying to solve two problems based on kinetic energy formula. See the first one, there is a body of mass 15 kg moving with velocity 4 meters per second. What is its kinetic energy? So it is very simple. Kinetic energy ke equals to half m v square. So half into mass is 15, v square is 4 into 4. So 2 2's 4. So how much this is? 15 2's 30. So 30 into 4, which is 120 joules. Is the answer. Now come to the second one. There is a car, it increases speed from 30 kmph to 60 kmph. Now you need to calculate what is the amount of work done. So work done form, force into displacement, but displacement is not given, force is not given. But still, how do you find work done? Yes, just earlier I have told you that amount of work done is the change in kinetic energy, ke2 minus ke1, final minus initial. So mass, velocity, you can find kinetic energy. So to find kinetic energy, what we do, first of all, we convert kmph into meters per second. I told you, we need to convert into SI units. So you take initial velocity u, which is 30 kmph. If you want to convert into meters per second, 30 into 5 by 18, and its value is 8.3 meters per second. Now final velocity v, 60 kmph. So 60 into 5 by 18, and its value is 16.67 meters per second. If you calculate it, you will get it. Okay, now initial kinetic energy, half m u square. So half into mass is 1500 into u square, 8.3 square. So if you simplify this, you will get, I will write here, 520.42 joules. Now, final velocity, kinetic energy, half m v square, which is 1 by 2 into 1500 into final velocity square, which is 16.67 whole square, and this value you will get 208417 joules. Now, the amount of work done, see this is equation 1. If you take equation 1, implies the amount of work done is KE2 minus KE1. KE2 208417 minus KE1 52042. Now, if you subtract it, what the answer will get? So you will get 156375 joules is the right answer. Okay, so you should remember, whenever you are unable to solve work done without giving force and acceleration, then you can apply work energy theorem. Now we are going to derive the potential energy. There is a body of mass m which is pulled up, or you can say thrown up against the gravity to a height h. So the gravity is acting downwards, Fg, but we are applying the same amount of force upward. Same amount of force upward to make the body to move to the height h. So as the gravitational force is nothing but the weight of the body, which is mg. So this mg, Fg, is nothing but equal to F, because both forces are equal but in opposite in direction. F equal to mg. Okay, the amount of work done, we know that W equal to F into S. So the force F equal to mg into S. S is the height, which is h. Okay, so this is nothing but potential energy. Of course, you need to take negative sign because you are moving upward with against the gravity. Thus, you can mention negative sign here. It is correct to mention negative sign, but magnitude, as potential energy is a scalar quantity, we can take only magnitude, which is mgh. That's the formula for potential energy. Now let us solve some problems based on potential energy formula mgh. See the first one. There's a person of mass 60 kg. He wants to climb up the steps. Each step height is 0.15 meter. Then what is the total energy required to go to the second step? So let us solve. So as moving upward is nothing but potential energy, because going against the gravity. So potential energy PE equals to mgh. So mass is 60 kg, g is 10 meters per second square. It's a constant value. Height is 0.15. So if you see 2 0 to cancel, 56, 90. So 90 joules is the answer, but it is only for one step. But for two steps, implies potential energy equal to 2 into 90, which is 180 joules. So he is consuming 180 joules to come here to here. Okay, here one important thing I want to tell you. Suppose he is going upward in the steps, but in another case he went directly up till here. In both the cases, in which case you have more potential energy? This case A or this case B? The answer is both cases you have the same potential energy, because potential energy doesn't depend upon the path how you have traveled, it depends upon the height only. So in both the cases the height is 0.3 meters only. 0.3 meters only in both the cases. So it depends upon height only, not on the path. So in both the cases P is same. The second one, a body of mass at 12 kg is lifted up to a height h. Then it has potential energy 480 joules. The question is, what is the amount of height it is raised? So you apply PE equals to mgh formula again. 480 equals to mass is 12, g is 10, height h. So height h equals to 480 divided by 120, 0 0 cancel, 12 fours are 48. So height is 4 meters. This is how you can apply the knowledge and you can solve the problems in potential energy. Now it's a time to understand the conservation of energy. In the previous chapter, I have told you about we have many conservation laws. In that one conservation law we discussed, which is conservation of momentum, and this is the second one, conservation of energy. What conservation of energy principle says? It says that energy is neither created nor destroyed, but can change from one form to another. Energy is neither created nor destroyed, but it can change from one form to another. This is the statement of principle of conservation of energy. That means how much of energy you have. If we lose the energy, we say that we lost the energy. Maybe you lost the energy, but lost energy is mixed in the environment, so that always energy is balanced. So energy remains constant. Let me explain the statement using an example here. A ball is here. A ball is at a height h. It is at point A. This is point B. So at point A, the final velocity, suppose we can say it's a freely falling body. When I say freely falling body, it's not final, it is initial velocity. Initial velocity u equal to 0, final velocity v is maximum. So at point A, what is the amount of energy the ball has? It should have same amount of energy at point B also. Let me prove. So at A, so first you take kinetic energy. Kinetic energy half m v square, but v or u is 0, so kinetic energy is 0. Now coming to potential energy, it is the mgh. H is the height from the ground. So h is height from the ground. So this is mgh. So total energy is Ke plus Pe, which is mgh. Total energy at point A. Now coming to point B. At point B, the kinetic energy. The kinetic energy Ke equals to half m v square, because v is the final velocity. But wait here. What is v value? We should know. So to find v value, we do a little calculation. See, we know that v square minus u square equal to 2as. U is 0, s is nothing but h. So I can write v square equals to 2gh. Why I mentioned g here? Because a is g. Body is falling down. A is acceleration due to gravity. So 2gh. So it's v square is 2gh. I can supply here. So it is nothing but half m 2gh. 2 cancel. So k is nothing but mgh. Now take Pe. When the ball at point B, the height is 0 because it is on the ground. Height is from the ground. But as it is on the ground, there is no height. So it is 0. So P is 0. So implies the total energy is again Ke plus Pe mgh. So see these two. Here the total value mgh, here also total mgh. So wherever you go, the energy is changing. At the highest point you have potential energy. At the ground point, you have kinetic energy, but the total energy always constant. So that's why conservation of energy says you cannot create it, destroy it, but you can change from one form to another. Let me give you some more examples. Electric bulb. We say that we are using so much of energy to lit the electric bulb, to function of electric bulb. But here also one form of energy converts into other form. So here the electric bulb converts electrical energy to light. Anything else? Yes, plus heat. Some sort of heat also released. That's if you touch the bulb after some time, you feel hot. Electrical bell. Here also electrical energy, yeah, converts to, yes, sound energy. Diwali cracker. How the crackers are made? Crackers are made by chemical energies. So here chemical energy converts to sound. Yes, you heard the sound. Light. Yes, you can hear the light also. Plus heat. Yes, they are hot, no? They are hot. Once the bomb is blasted, if you touch the bomb, you feel hot. When the bomb blasts, you can see some sparkles, light, and you hear sound also. Generators, AC generators. Generators are the one which generates electricity. So how it is possible? They convert mechanical energy to electrical energy. Mechanical to electrical. Motor of a fan, motor of an air cooler, motor of any mechanical device. Motor does the reverse action. In motor, the electrical energy converts to mechanical. In fans, if you see, there is a motor inside. When you switch on the fan, it takes electricity, the blades starts rotating. So blades rotation is mechanical. So like there are so many examples. It tells that energy is actually not lost. It is changing from one form to the other form. So far we learned about what is work, what is energy, how work energy both are related, and especially we learned about kinetic energy and potential energy. You have given two machines. These two machines are doing some X type of work. The thing is, the difference is machine 1 performed the work in 1 minute. We have given the same work to machine 2 also. But machine 2 performed the same work in 1.5 minutes. Then if I ask that which machine is the better one, you will say obviously machine 1. Why? Because machine 1 performed the work faster than the machine 2. So this faster or machine 1 is the efficient than machine 2. This faster efficiency depends upon their power. So machine 1 is more powerful than machine 2. So here our concept is power. So how do we measure the power? So power is defined as amount of work done in unit time. Amount of work done in unit time. Amount of work done in unit time. This is one definition. One more definition is there. It is the rate of energy consumed or rate of energy consumption. So in that case, power formula is energy by time. So you have two types of formulas: work by time, energy by time. And if you see the SI unit of power, it is watt, W-A-T-T, in short form capital letter W. James Watt. After his name, we kept SI unit for power. And if, according to the formula, you can write 1 watt equals to 1 joule per second. Because work unit is joule, time is second. So 1 joule per second. So this is, you can say 1 watt equal to 1 joule per second. That's the power formula. If you see the expression work by time, lesser the time, more the power. Because power time both are inversely proportional. So less time, more power. So that's in the beginning, the example, if you see in this 2, this is less time. That's why you have more power for the machine 1. Now let us apply the knowledge of power in these examples. There is a crane whose power is 300 watts. And this crane lifting 10 kg block and keeping on the 4th floor of a multi-story building. So each floor has height 3 meters. And this 10 kg has to be kept on the 4th floor. This is the case. Now it is keeping the 10 kg weight to the 4th floor in time 5 seconds. The question is, what is the power to lift the 10 kg to the 4th floor? So whenever we say power, you know the power equal to energy by time. or you can say work by time. Where the body is lifting up, it is against the gravity. Therefore, the energy is potential energy by time. So this is mgh by time. So the mass is 10 kg, g is 10, acceleration due to gravity, height 4 floors, 1 floor is 3 meters, 4 floor is 12 meters, 12 by time is 5. So this is 1200 divided by 5. So if you divide it, 5 2 is 10, 20, 4 for 40, so 240 watts is the power. Okay, now here one more interesting question. If I ask, what is the efficiency? What is the efficiency of the crane? How good it is? Then how do you find? So efficiency, if you want to find, the formula is output power by input power into 100. Remember this formula. Output power by input power into 100. Okay, so efficiency equals to, what is output power? So how much of work it has done, in that how much of power it has consumed. This is output power 240, but actually crane has 300 watts of power. So output power 240, input power is 300 into 100. So if you see 2 zeros cancel, now you get 80. So the efficiency of the crane is 80%. It's not 100%. Then what happened to the rest 20%? The 20% of efficiency, that 20% is energy wasted in the form of heat. So it can do only 80% of work. Correct. The next one. You have applied 0.3 newtons of force on a block, and the block moves with the velocity 2 meters per second. What is the power? So power formula, energy by time. But where is the energy? Energy is not given. Potential energy by time. It is not going up. So potential energy can't use. So what to do? See, P equals to work by time. Work is also called force into displacement, as we know that, by time. But if you see here, S by T, distance by time or displacement by time. Displacement by time is nothing but velocity. So power has another formula, F into V, force into velocity. So therefore power P equals to force 0.3 into velocity is 2. So it is 0.6 watts. So power is work by time, power is energy by time, power is force into velocity also. Now we're going to discuss about a real application of power, that is electrical energy calculation. Every month you will get an electricity bill. In that bill mention that 200 units you have consumed or 300 units you have consumed, and this is the so and so amount, and you are paying the amount to the government, electricity department. But the thing is how they calculate the number of units you have consumed at your home. So let me tell you, let me explain you how you can calculate. Generally, electrical energy unit is kWh, kilowatt hour is a unit of electrical energy consumption, or you can say 1 unit equals to 1 kilowatt hour. If you consumed 300 units per month, it is nothing but 300 kilowatt hours. So power P equal to energy by time implies energy equal to power into time. Okay, small t. Now power into energy equal to power into time. Now you see kilowatts, what is the power? So kilowatt, kilo means 1000 watt into time is hour. 1 hour is 60 minutes. 1 minute equal to 60 seconds. So if you calculate everything, you will get 36,000,000 joules, or simply I can say 3.6 into 10 power 6 joules, right? So this is what 1 kWh value. So if you consume 1 unit at your home, by lighting the light, by switching on the fan, or watching the TV, or watching the working with the refrigerator, laptops, computers. If you consume 1 kilowatt hour or 1 unit, this much amount of joules of energy you are consuming. Good. Now, how do we calculate if we use the bulb for 10 hours, if we use the fan for 8 hours? Let me tell you. So, there is a house. In that house, you have a fan. Okay, this fan is working. There's a fan. Okay, and there is a bulb. It's a bulb. Let us say fan has 60 watts power. Bulb has 40 watts power. Fan is used for say 15 hours per day. 15 hours per day, and bulb is used for 10 hours per day. This is an example. Now, the question is, how many units consumed? This is the first question. How many is consumed? So let me calculate. So for the fan, energy equal to power into time, and power of a fan is 60 watts. 60 watts into time. 60 watts and time is 15 hours. 15 hour. Now what we do here, little tricky we play, the mathematical trick, because we know that 1 unit is kilowatt hour. Convert this number in terms of kilowatt hour. After substituting this, you multiply kilo, divide by kilo. Then what happens? 15, 6, 90, 900 kWh by K. K means 1000. So this is how much? 0.9 kWh. That means you have consumed 0.9 units per day for fan. Apply the same concept for bulb. So energy equals to, the bulb power is 40 watts. It is used for 10 hours per day. 10 hours. So this is 400 watt hour into K by K. So 400 by 1000 kWh. So 0 cancel. So it is nothing but 0.4 kWh. So how many you have consumed? 0.4 units per day. So total units, let me write here. Total units you have consumed is 0.9 plus 0.4. This is 1.3 units. So this is how they calculate automatically. 1.3 units. Now still, if I add more questions to this case, say 1 unit cost equals to 2 rupees. 2 rupees. Then how much he has to pay? Implies 1.3 into 2, which is 2.6 rupees per day. Per month, if it is per month, then how much he needs to pay? You know that. Stop this video and do the calculation. Play again and check the answer. So for a month we take 30 days into 2.6. So how much this is? 0.1817. So it is nothing but 78 rupees per month. That's how we can calculate the number of units you consumed and the amount you need to pay. So far we discussed about the different concepts in this chapter, starting from work, energy, power, and how to measure the consumption of electricity, etc. Now this is the time to use our knowledge to solve problems. So the first numerical for you: an object thrown at a certain angle to the ground moves in a curved path and falls back to the ground. The initial and final points of the path of the object lies on the same horizontal line. What is the work done by the force of gravity on the object? So it seems to be a big question, but it's not a very big question if you frame the whole question in terms of a pictorial representation. See here. So there is an object. This is the ground. So this is the ground, and it has thrown, we are making some angle to the ground. So let's say the point A, it's thrown and it describes the curved path and falls onto the point B on the same horizontal line. Now they're asking what is the work done by the force of gravity. For work done, W, the formula is force into displacement, as we know. Here the force is the force of gravity. Force of gravity is actually acting downwards. So you need to see the work done, if any work done is done in the direction of force of gravity. Okay. I want to find that the total path from A to B, it is nothing but distance travel, as you learned in the first chapter. But in the work done formula, it is the force is a vector, displacement is also a vector quantity. So here you shouldn't take the distance, instead you take the displacement. When we take displacement, we say starting point, ending point, and the shortest distance between starting and ending point. Let us write, let us locate C, the highest point in the path. Then from A to C, so A to C, this is the height reached, A to C, in this way. C to B, the displacement, the same height but in this direction. So from A to C, AC, the height reached is H. C to B, again the height covered is H. C to B equal to H. But the only difference is, as is displacement, the C to B is opposite to the first one. So therefore we need to keep minus H. Then the total displacement is nothing but AC plus CB, which is equals to 0. H minus H equal to 0. So therefore the amount of work done by the force of gravity is F into 0, which is equals to 0. So there is no amount of work done by the force of gravity. Now the next problem for you. A battery lights a bulb. Then you need to write the energy changes taking place. So this is the bulb, but this bulb is connected to the battery. So say this is the battery. The battery has two signs and the battery is connected to the bulb. Now what type of energy is taking place? Generally you know that when you have the bulb connected to the top of your side wall of the ceiling, and if you switch on from the main board, the lights glow, and you know that is because of electrical energy converts to light energy. But here a small difference, we are not connected to the main supply, we are connected to the battery. Now from the battery, some energy is converting into electrical, and that electrical energy goes to the bulb, making the bulb to glow. And the question is, what is the energy the battery actually converting into the electrical energy? Yes, there it is. It is nothing but chemical energy. So in the battery, the chemical energy turns to electrical energy. Now the electrical energy supplied to the bulb, and the bulb glows. Therefore the bulb glows means it gives light energy to you, and after some time if you touch the bulb you feel hot. That means in addition to the light energy, you are also getting heat energy. So therefore the electrical energy converts to light and heat. So this is the energy conversions happening, and here we can confidently say that energy is conserved, energy is not at all wasted. So chemical to electrical in the battery, and in the bulb it is electrical to light and heat.